And I think it was the wrong pointer. So okay, so that's visible. Great. Okay, so as I was saying, I think I just realized looking back that the last time I was in the MagLab was almost exactly 15 years ago. And that time I came, I think, for 2 days, and then it happened to snow in Florida, of all things. And so I got stuck here for 2 extra days. So let's hope that this time that doesn't happen. Although it's nice and warm compared to being in the UK. Okay, so let me start by saying that I'm going to talk about work, some of which is unpublished. Some of it is in collaboration with Andre and his group. But most of the heavy lifting and what I'm going to talk about was done by Dumitru Kalugaru and Konstantinos Vasiliou, who are both a student at a postdoc at Oxford in collaboration with some Monte Carlo experts at other places. So what I want to do today is sort of remind you a little bit about some moiré background. I know it's coming a little late in the workshop. I just wanted to give you a personalized view of what I think is interesting as a materials platform for moiré, and use that to motivate a new class of moiré materials. So I'll sort of take a little bit of a historical view on where we stand with moiré graphene and say maybe why I think it's a good time to look at a new class of moiré systems. So just to remind ourselves, we've seen this and, lots of experimental talks. So one of the large power of the moiré platform is the fact that we have these materials that are held together by very weak van der Waals forces. So the very fact that you can take notes with your pencil means that those van der Waals forces are weak enough to strip individual layers. And that means that we can reassemble them in interesting ways, and we can create a moiré potential by working at some very small twist angle. So as a useful heuristic, the kind of typical moiré length scale is something like 2 pi over a lattice spacing. That's a typical moiré modulation for a microscopic lattice. And for a moiré lattice, it's just suppressed by a factor of the angle. And so you find a moiré length scale, which is like the microscopic lattice spacing over a small angle theta. And that typically is on the order of 10 nanometers. And so as we've seen, just like a magnetic field, and we'll do some examples of this, just as magnetic fields modify kinetic energy of free electrons, moiré modifies the dispersion of the electrons. And so you get an emergent band structure, which often has interesting properties. And much of the excitement is that one can enhance the correlations because you can get flat bands as kinetic energy is vastly suppressed relative to the bare kinetic energy of the individual layers. And of course, there are many possible combinations and parameters that give us route to new physics. So the goal of this talk is to sketch one possible route to new physics that I'm particularly excited about. Okay? And so let me just say one last feature, which is in some sense experimentally why the moiré setting is such a powerful platform. So if you give me and there's a nice back of the envelope calculation that I like that tells us why that moiré length scale is a rather convenient sweet spot for doing lots of interesting experimental work. Okay? So let's imagine I have a 2D material, a very natural instinct, and this is something that's gone back for many years to when people were doing semiconductor fabrication and things like the quantum Hall effect, is that you could electrostatically gate your sample. So that basically amounts to saying, I think of my sample as one plate of a parallel plate capacitor, I have some gold backgate, and I establish a voltage across that of some V. And let's imagine that I have some typical numbers. So the spacing is about 10 nanometers distant between the gates. I've got a dielectric constant of about 10. And let's say as a figure of merit, the voltages I can apply are of the order of a volt. Because if I do more than that, much more than that, I'll start doing terrible things to the sample and destroying the material over there. So I don't want to do much more than about a volt. So you can just ask yourself, given these numbers, what kind of charge density can I create just by setting up this problem, right? So it's an elementary problem we could give, even to pre-med students. And, hopefully if they got it right, you would let them operate on you. If they didn't, you would, maybe save your life. So the calculation is pretty easy. You write down the charge density, which is Q over A. But we know that the charge is just the capacitance times the voltage. And so just plugging in the capacitance, you get a nice formula that relates the dielectric constant or relative dielectric constant, the voltage and the distance. And if you want, if you work this out, what you find is that typically you can put about an electron in a square of size 10 nanometers into the sample. I'm being fast and loose with numbers. There's an order of magnitude estimate. And if you actually think about a microscopic lattice spacing about a third of a nanometer, this is 1,000th of a unit cell of electrons that you can dope into the system. So if you give me a microscopic lattice, by electrostatic gating, I'm just moving charge around in a very, very small amount. So I can't actually fill or empty entire bands by doing this. It's just impossible, just the numbers given there. But what this means is that if I've got the typical moiré scale, if I created a lattice which has a 10 nanometer length scale, that's the figure of merit for fully filling or fully emptying its bands. And this is why by just dialing a knob, I can tune you across an entire filled band and tune metal insulator transitions. So in a sense, this kind of versatility of being able to sweep phase diagrams very easily is in some sense intrinsic to that 10 nanometer moiré length scale. It also happens to be a length scale at which we have lots of nice access to various probes. You have to push the limits of things like STM, but you can actually, in the sense of being phase coherent across that, but you can actually do beautiful STM experiments that interrogate individual unit cells and then phase coherently look at what happens in adjacent cells, and that's very powerful. And since the moiré bands are also weakly dispersive and often wind non-trivially, we get sort of for free topology and correlations alongside this tunability, right? So this is something that should be familiar to all of you, but I think it's worth remembering that as we ask about what other things that we can do. Okay? And of course, the field was kicked off by what I like to think of as the hydrogen atom of moiré materials, and that's a sort of loaded comparison. It's hydrogen in the sense that it's simple and we can do a lot of calculations for it on the back of the envelope, but it's also like hydrogen in that it's very special, so twisted bilayer graphene. That's because you have a linear Dirac dispersion, so there's sort of a special structure to the moiré problem, and much has been written about that. But this goes back to the very early idea that the moiré reconstructed bands are almost perfectly flat near a magic angle of about 1.5 degrees. And this was pointed out by Bistritz and McDonald. And we have these 8 central bands with flavors of spin, valley, and sublattice degrees of freedom. And much of the excitement was that, again, because of the ability to gate, you can push the electrons, you can sort of fill or empty these 8 flat central bands, and you look for enhanced correlations in that setting, right? And just to give you a status report of TBG to say why I think it's a good time to go on to other things, in some sense, if you look at the first experiments, I'm going to show you sort of the 2 puzzles from the first pair of papers that arguably kicked off at least the current era of interest in the moiré phenomenon. The first puzzle was that one saw correlated insulators within that octet of 8 bands. But since that was the band theory, the gaps I showed in the previous figure were the predictions of band theory, there needs to be an explanation for why these systems become insulating. And that explanation has to come from interactions. That was the first puzzle. And of course, the second and even arguably more exciting puzzle was that if you doped those correlated insulators, you got a superconductivity that was accessible by gating, right? And so these were the sort of 2 puzzles from the early days. So what's a status report on where do we stand, let's say 7 years or almost 8 years since those first papers, where do we stand on answering those 2 puzzles? So as a sort of report card to ourselves, and so I should say there's also a wide range of other related phenomena, but they're sort of tied to one or other of the sort of 2 key underlying puzzles. So I would argue that the first of these puzzles, one could say, has been mostly resolved. We've got a lot of understanding that the topology and the symmetry of the moiré bands in TBG are quite special, and their interplay gives you an approach. One way to think about it is you can link it to quantum Hall ferromagnetism. There's another beautiful way pioneered by Andre and by many other people since then, which is the heavy fermion approach. But either way, we have ways to think about this that are somewhat different from the traditional Hubbard model approach to correlated systems. And what that has led to is the understanding that the generic correlated insulator in nearly all samples appears to be something called the incommensurate Kekulé spiral. This was predicted theoretically by our group at Oxford some years ago and has been seen in STM in a pair of experiments in twisted bi- and tri-layer graphene a couple of years ago. And while there's a specific prediction of where these spiral orders come in, we sort of understand quite well how they compete with other correlated states and where they fit in. So I think that we would argue that the correlated insulating states, we have a fairly refined understanding of what they're doing. On the other hand, what about the second puzzle? Superconductivity, I would argue, is also largely open, and unfortunately, in some sense, is approaching what I like to think of as the cuprate limit, where the number of theories is much larger than the number of experiments, which is much larger than the number of agreements between theorists and experimentalists between themselves. So this is a limit where I'm scared to be, so it may be time to think about other materials, given that this didn't go so well for the cuprates in some sense. It becomes very difficult to have a concrete understanding of what's going on when there's so much happening. I still think there's interesting questions there, but it may be time to look at a new class of moiré system. And so that's the goal of these lectures, which are taking the first, if you like, theoretical steps towards talking about a new class of moiré systems. And what I'll do is sort of give you a pair of lectures. The first of them will really be recapping work by Andre's group and others in proposing a class of moiré platforms. And the second will be more unpublished work that takes a first stab at addressing the role of electron correlations there. Okay. So, of course, it's not to say that TBG is far from the only moiré platform. After all, there's a whole moiré materials universe now. So one thing we can think of is TBG, the most famous example, is a HOMO bilayer. The two layers are the same. And the very natural thing you can do is stack two layers on top of each other and then twist them, because that's the way you can generate a moiré pattern with the HOMO bilayer. And so in addition to TBG and all its various cousins, we also have TMDs. So for instance, we have twisted MOT2, which famously was one of the first observed was arguably the first real fractional churn insulator seen in experiments. But we can also take heterobilayers, where you have two different materials in each layer, and then you don't have to twist to create a moiré pattern. You can just stack, and the lattice mismatch will do it for you. And there, of course, we have examples like WSE2 on WS2, which gives you sort of Wigner crystal-like states. We have Kondo lattice type regimes for other TMDs. And you can see that there's a whole variety of states over here. Right? So there's this entire universe. But what underpins all of these, if you unpack what's happening in each individual layer in all these examples, is that if I plotted the Brillouin zone of these layers, these are all hexagonal lattice materials. And if you think about where the action is happening, it's typically happening at the K points for nearly all these examples, and a small set of examples at the gamma points. But the Brillouin zone is a big space. There are other points where the single particle dispersion can come in. So this is what I want to talk about today. And so in graphene or most TMDs, each layer has low energy states near the K points, the Brillouin zone, right? So that's where you start off with. The monolayer has a dispersion, which is at the K points of the Brillouin zone. And moiré reconstruction produces two valleys, because you do moiré around each valley separately. And each valley has a pretty two-dimensional dispersion. That's what we got for doing TBG. That's what we get for doing MOT2. There are all the other complexities of topology and other things that can enter, but this is sort of a well-studied problem. We could also twist layers whose low energy states are at other points, for instance, the M points. And so what I'm going to tell you about in this lecture is what happens when we do, these pair of lectures is the story of what happens when you twist in the M points. And so the starting of that story. Yes, that's what I want to try and, that's the setting for what I want to do. And so here's a plan. The first lecture is I just want to recap the basic story of moiré reconstruction. So one way of thinking about it is that, I've been doing moiré on TBG for a long time. You kind of do this calculation and you do it. But when you want to think about placing it within the context of doing moiré for a wider range of problems, it forces you to go back to first principles and think a little bit about, and go back to first principles, not first principles DFT, but first principles of how you did this calculation. It forces you to go back and think about how best to set up a moiré reconstruction problem. And so I think these papers of Andre's group and others, they have a lot of detail, and they gave you a very nice way of thinking about how to do the moiré problem, which actually goes back to the original ideas of Bistritz and McDonald, but I think gives you a nice systematic understanding of how to make this work at various different symmetries. In the second, I'll talk about some of the fact that these endpoint platforms, in some of them, have kind of very nice access along special axes to being able to be simulated by, in some sense, the gold standard for many-body quantum simulations, which is sign-free Quantum Monte Carlo. And I'll tell you a little bit about how two different sign-free Quantum Monte Carlo methods can be brought to bear on this problem. Right? So that's the plan for this pair of lectures. So let's go back and talk about moiré reconstruction. So, by the way, I should say that since I'm going to build this up slowly, I know that the idea was to defer questions to the end, but since one thing builds on the other, I'm happy to take the odd question right now. I don't think I have quite enough material to pack the whole hour because I planned for that, so that's okay. But if I think I'm running out of time, I'll sort of speed up. Okay. So this is when I'm actually doing substantive work. The rest, the stuff until now was just sort of a review. So we know that the origin of the moiré band schematically is like this. We have some untwisted problem, and when I twist, apart from just twisting the single particle problem, I also generate a moiré potential that I can think of as being obtained from a sum over some set of momenta in a moiré reciprocal lattice. And so the question that I want to do is ask how, with the original problem, let's imagine K lives in the full Brillouin zone of the microscopic problem, K with this twiddle. What I want to do is think about the problem now that I had, if you like, in this problem, I had some original Brillouin zone and I twist it. So now immediately there's a subtle complication. This has some Brillouin zone. This moiré potential has a Brillouin zone. They may not necessarily agree, and that just is the fact that unless I choose a very special twist angle, the moiré potential is incommensurate with the original lattice. But for very small twist angles, effectively, we can ignore the periodicity of the dispersion within a single layer. Operationally, this is because if I'm only interested in physics near the Fermi energy, all that's happening is the reconstruction is happening within a very, very, very small patch of states near the Fermi energy. And for those states, the microscopic Brillouin zone might as well not exist because you're never going to know about that on the moiré reconstruction scale. So in coupling them together, I can effectively just take a continuum limit in each layer and ignore what happens within the layer that the bands will eventually turn over. So if you like, all moiré problems in this sort of continuum, the reason we think of that as this continuum model is really, the idea is what we're saying is, we're doing the old kind of Ashcroft-Mermin solid-state problem of nearly free electrons, except that we start off with whatever we got from the individual layers. And then it's a band folding problem. And so this allows us to define a notion of a moiré-Brillouin zone. This approximation allows us to define a notion of the moiré-Brillouin zone, even if the problem is incommensurate. And that means that we can do reconstruction for each valley within a single layer. So since they don't mix, the two valleys won't mix. And so this is important to remember because this is where a lot of the emergent symmetries come from if you take this continuum model limit, because various things like valley, for instance, is not really a continuous symmetry, but in moiré, we traditionally promote that to a real conserved quantity, not a discrete lattice symmetry and so on. So in the generic moiré problem then is just a band folding problem. And so we want to come up with a systematic way of understanding that band folding problem. But it's also a somewhat special band folding problem because of this layer index. So it's this band folding problem, but it has these off-diagonal terms. And often we care the most about those terms because, after all, anything that happens at the top and the bottom is just sort of effectively renormalizing the single particle problem. So very often, and in particular in the case where the two layers are identical, we sort of want to think about the dominant physics as being carried by these off-diagonal terms, and that makes this an interesting problem to try and solve because of this additional structure. So this band folding problem can be rewritten in the form of a K-space hopping problem. And this takes a little bit of work to do, but what you argue is that you just Fourier transform and just follow your nose through. And what one can write down is to say, well, in the end, I know that my problem, the only really good conservation law, since I put on the only really good translational symmetry is moiré translational symmetry. I started off, and remember, I've thrown away the microscopic translational symmetry. So then the K, which was originally allowed to go from, in this continuum limit, I just assumed K goes from minus to, in this picture where I threw away the microscopic Brillouin zone, K runs from the K twiddle that I wrote on the previous page runs from minus to plus infinity. But the only conserved quantity is a crystal momentum that has to live within the moiré-Brillouin zone. So that's what I'll call K without a twiddle. And so I've got a block, I must have a block Hamiltonian for each of those Ks. But then when I take my original problem and fold it back, when I take my K and write it, I can take any K twiddle and write it as some combination of K and Q. And that allows me to label all states. But then the Hamiltonian will now be off-diagonal in this reciprocal index. So this Q and Q prime are points that live in a momentum space lattice. And if I was just doing reconstruction in a single band problem or something like that, then these would necessarily be just, this Q's would be the same as the G's I wrote on the previous page, the reciprocal lattice. But it turns out that a very useful way to think about different problems, actually originally pointed out by Bistritzer and McDonald, is to actually think of this momentum space lattice as being a little bit more general than just a reciprocal lattice. And the reason for that is, in some sense, there are two gauge choices of this problem. Because notice that I have this CKQ, and this I is just some index that has all the internal indices. This CKQ is just basically saying something about the total momentum referred to the Brillouin zone, but then I need to take Q to map it into the original microscopic problem. And so the final momentum will be something like K minus Q. And so there's a question of where to put the zero in each layer, because there's a kind of gauge choice in how I measure momentum. The common choice, which is actually what I often do numerically when I'm doing these kinds of calculations, is to just pick K minus Q from the gamma point in each layer. But then every layer will agree, at this level, we can impose some symmetries and put the same gamma point for all the layers. And so I have some problem like this, and the Q lattice will then coincide with the moiré reciprocal lattice. There's just G's because there's nothing else I can do, right? But that will obscure some structure, because if I wrote this matrix with G's as its indices, for the right set of problems, there'll be some internal structure, and I may struggle to find that. So an easier way to do it is to pick a slightly different gauge choice, where in each layer, I measure this K minus Q from a momentum, which is where the valley lives in that layer. So I'm imagining a single layer where the dispersion is emerging from some pockets in momentum space. So if for TBG, for instance, these valleys in each layer, in valley eta, in the top layer, it'll be the rotated position of the K point and the rotated position of the K point in the other layer. So one will rotate by plus theta over 2, the other will rotate by minus theta over 2. So this means that when I set K minus Q to 0, then the dispersion goes to the minimum. In the earlier one, I'd have to pick a big number because I measured everything from the gamma point. And so this gauge difference is captured by how I map between C to the microscopic moment. Okay, so there's just some gauge choice. But it turns out that this, while they're equivalent, and the first one, to me at least, is more intuitive. It just, follow your nose and you get that. The second choice actually makes various aspects much easier to see. And so I'm going to use that in the rest of this talk. I see Andre is inspecting me carefully, so if I make a mistake, I'm sure he'll correct me. So let's just go back and look at the moiré reconstruction. I want to set this up as a recipe. And so we've got a K-space hopping problem, and I'm going to work in the shifted gauge. So is this roughly clear what we're doing? We're just doing a band folding problem. We're going to set up the band folding problem in a way that allows us to do this more generally. So I'm going to work in this gauge where I measure K minus Q from the position of valley eta in that layer. And in this case, it turns out that we'll see that the Q lattice will encode, in some sense, the specific monolayer, where the monolayer dispersion is doing interesting things. So let me set up a hierarchical procedure. So the first step we'll see is the easiest one. We just want to fix the moiré reciprocal lattice. The second step is going to be some geometry, and it's going to be different for the gamma, K, and M points, is to fix this Q lattice, the lattice of things that enter. So there's a momentum space hopping problem between momenta Q and Q prime. And so what I'm going to think about is how to fix the Qs and Q primes that enter. What is the momentum space lattice on which we're hopping to work out the dispersion at each K? Steps 3 and 4 actually go hand in hand in order to actually understand all the details of how the reconstruction proceeds. So these are just sort of kinematic. 1 and 2 are just kinematic geometric things. But 3 and 4 actually involve solving some real problem of hoppings and things. These need some physical inputs. And one of them is to think about identifying exact and approximate symmetries. And the other one is to obtain HQQ prime and diagonalize. And sometimes what you do is do this, make a guess, look at the continuum model that you get, and you infer some symmetries and you realize there was some approximate symmetry that you missed. So often 3 and 4 sort of feed back into each other. And if you think about the information that you need, we get sort of go from needing less specific things that are very general to more and more specific. And the level of modeling, and it's unsurprising because the level of detail in our modeling gets more and more. So for instance, the first step, all we need is the monolayer lattice vectors. For the second step, we actually need to know where the monolayer minima are. For the third step, we need sort of more broad details such as stacking arrangements. And to actually get HQQ prime, often you need some input from ab initio in some way or some other way of computing interlayer tunneling matrix elements. So if you like, if you're kind of thinking in general terms, this is the kind of protocol that you'd follow in sort of going from thinking abstractly about a material all the way to thinking about how to compute its span structure. Okay? So I'm just going to go through these steps in turn.
Thoughts to the two layer.
Not to the two layers. No. Q and Q prime are so H is a matrix in the layer index. I and J are layers. So Q and Q prime are just the following. So at each point in momentum space, I do band folding. And so K is, in this language, K is a good quantum number. It lives in the moiré reciprocal lattice. It lives in the moiré-Brillouin zone. So Q and Q prime, they fold the bands, and I think about all the matrix elements of the original problem that can come in.
They have the same set of momentum.
They're the same set of momentum. So Q and Q prime, so when I meant Q lattice, I should probably use the curly Q. They're drawn from some particular lattice, and we'll see how to compute that lattice now. Okay? Yep.
When you will give you the buzzer, you will bring the
Yeah.
what the first one is that you take it from the gamma point.
Yeah.
Of the
Of all of them, right? Because I just think of some symmetry that allows me to fix all of them to have the same gamma point. And so that means that they all share the same origin. All it's saying is that if I measure momentum, in one of them is a common origin for the momenta. In the other one, I'm saying, oh, when I measure the momentum of the state from this layer, I refer it to the minimum of that layer. So, for instance, in graphene, this is actually, if you like, the Bistritzer-McDonald choice in their paper. They measure the momenta in the upper layer from the Dirac point of that layer and the lower layer from the Dirac point of the lower. But since they're displaced, there's a mismatch. And we'll see that P, if you had the dispersion starting at the gamma point, those two gauge choices coincide. It's only if the dispersions are away from that, and that's why it's going to be interesting.
first choice is like if you have a moiré gamma.
Yeah.
Right.
The first point, yeah, it would be just pick it at the moiré gamma point. I'm going to assume cases where there is a moiré gamma point, and I can define it, right? Good? Happy? Okay. So let's fix the Moiré-Brillouin zone, and this is actually pretty straightforward for small twists. So I consider two identical lattices related by a twist. The first reciprocal lattice I'll think of as the reciprocal lattice of the first layer I'll think of as being generated by some primitive vectors b1 and b2. The second lattice will be generated by primitive vectors, which is just rotations of those vectors by theta. That's just because I'm just choosing those two. And if you think about the usual Moiré problem, what I do is think about the periodic potential generated by this, the periodic potential generated by that, and look at the smallest difference. And for small angles, you can convince yourself it's just the difference between this primitive and that primitive vector, because I do a small twist. So that means that the Moiré reciprocal lattice is generated by essentially r of theta minus 1 times acting on bi. So just r of theta b minus b. And for small twist angles, I just expand the rotation matrix, and I can write it as 1 plus, keeping to linear order, it's 1 plus theta z hat cross b for small twists. You just do this just by expanding it out, and I've just used the off-diagonal terms and just encoding what a cross product does for you. And so plugging that into this formula, I find that the Moiré reciprocal lattice vectors are just the monolayer lattice vectors rotated by 90 degrees and scaled by theta. So if I start off with a problem like this, I end up with a problem like that. That's the way. So it just tells you that the geometry is if I start with a triangle lattice, I end with a triangle lattice for small twists. So this is a nice way of just thinking about, we're just reminding ourselves, this fixes the Moiré reciprocal lattice, right? So that's a good starting point. So the next point is to fix this Q lattice. And so this I think will clear up any of the confusions. So let's think of this shifted gauge. So I have CKQ and, eta J has this form here. And what I'm going to do is, imagine I tunnel from, in this problem, I want to think about this. This is a tunneling matrix element after all. So I want to think about an electron why it's a tunneling matrix element is it's just that the Moiré potential is scattering electrons from one momentum to the other. So I hit the Moiré matrix element once, and I tunnel an electron from KQ1L1 to KQ2L2. And if I unpack back to the sort of, if you like, the lab frame, the electron has to physically change its momentum from this thing to that thing, right? But remember, K is a good quantum number, so it's shared in the two problems. And sorry, this should have been Q2. See, there's a typo there. Should have been Q2. So K is shared between the two. And because I have Moiré translational symmetry, for this to make sense in this problem, this difference needs to be a Moiré reciprocal lattice vector, right? That's the only allowed terms in the hopping problem. So I have that this thing should be equal to this thing up to a Moiré reciprocal lattice vector. But since K is referred to the Moiré lattice, I can just cancel it out on both sides. Now, if I didn't have these PL1 eta and PL2 eta, it would just tell me that these Q1 and Q2 must differ by a Moiré reciprocal lattice, if I didn't have the layer freedom or this flavor freedom. But because I have that, there is this offset, and I can see that I have a rule that Q1 and Q2 must satisfy this generalized construction. In a regular material or just regular periodic reconstruction, I wouldn't have this offset. That just wouldn't be there. So this offset plays a very, very important role. And if you think about it, that offset is just, if you like, the distance once I rotate between the active points in the two layers. So in the gamma point, that distance is 0. But in the K or M points, there will be a non-trivial distance, right? And that's going to be where the important physics comes from. So this Q lattice, another way of thinking about this is it tells me that this momentum difference cannot be a moiré reciprocal lattice vector. You can also convince yourself this thing can't be bigger than a moiré reciprocal lattice vector because it'll absorb it. Any fractional part will just get absorbed. So it's something that's left over from the moiré reciprocal lattice. So that means that this Q lattice must have sublattice structure beyond moiré translation. It can't be just the set of points that you get from moiré translation, which would just be the reciprocal lattice. So fixing the Q lattice amounts to figuring out that sublattice structure. And a lot of nice symmetries are very manifest in that language, as was pointed out by Andre and Dimitri and others some years ago. So let's just, yep.
You
can think of, sorry? Sure, but then no, but it's just the rotated position of the Dirac point in that valley. That's why we set the 0 to be. So in the end, P could be large, but you'll only have differences of P, so it doesn't really matter. Yeah, you're right that it could be K and K prime, but in the end, I'll only care about the differences of P. Yes.
Right.
No, but if it was much larger than G, I can always take away any fractional part, right? So think about 2 K points. I rotate by a small twist angle. That's going to be much smaller than the moiré lattice. You can check that because that's sort of set by theta. Yeah, another question?
All right, go ahead. What happened?
Yeah, that's what I'm going to do now. Yeah. So if for gamma point, the 2 gauge choices exactly coincide. There's no such difference. So if the low energy physics was at the gamma point, like in valence bands of TMDs, then the Q lattice is triangular and it's exactly the same as the moiré reciprocal lattice. There is no difference because there's no extra structure there, right? And so exactly as you said, that was what would happen. And let's do the familiar case of moiré. So moiré, and this is the question that was asked by the gentleman sitting behind you, you pick this PL eta to be the rotated K point in this valley. So you have this shift. You're right that it's a big, it's this K point of the moiré problem. But you notice that the small difference between them is just something that's smaller than the moiré unit cell. And so you see that this thing is going to be smaller than, you can just check that this will always be smaller. And so if you think about this, this is the offset that you get is this vector Q1, if you like. And so if I go back to the previous slide, my reciprocal lattice will be generated by the points, the Q lattice is generated by the reciprocal lattice, which are the blue points, plus the set of points obtained by displacing them by Q1, which are the orange points. And so your momentum space hopping problem follows a honeycomb lattice, and that's what the Q lattice gives. And this is something that we know from graphene and the conduction bands of TMDs. Okay, so setup clear? Okay. Now, the next thing you can do is think about how this works for M-point twisting. This is the thing I care about, so I'm going to go slowly here. So let me pick it to be the rotated M-point in valleys eta equals 0, 1, and 2, and I'll count valley. And by the way, these etas for graphene, it's nice because I can just do plus or minus. Of course, since if I have 3 of them, I'm just going to do 0, 1, 2, and then count everything modulo 3. So 3 goes back to 0. Okay? And so the CKQ eta L, I'm going to write it in terms of the original problem as this rotation plus K minus Q comma L. And notice I'm suppressing an eta. I'll often suppress an eta. We'll see. And you can actually read off what eta should be without having to keep that index explicitly. So it's a little bit busy, so bear with me. I have the blue layer and the red layer. They're rotated relative to each other. So those are the K points of the layer. So if I was doing graphene, I would be talking about those points. I've just, to not make it busy, I've chosen not to draw that here. Shaded as the moiré-Brillouin zone. Notice that I have the M point of the layer. And you know how in graphene, the K point of graphene folds to the K point of moiré. Similarly, the M point folds to the M point. If you work it out, you'll see that happens. And you have now the M point of the blue layer, the M point of the other layer. And I've already, I think, convinced you that the shift that you have to capture has to be the M point has to come from that layer. There's another shift, which is Q1. And there's a third shift, which is the sum, which is not independent. It's Q1 and Q2. And you see that those are the 3 ones. And notice that each shift involves the difference between a pair of M points. So if you like, every time I do a rotation, one of the M points doesn't come in. There's a kind of rule of exclusion just because those are the smallest differences I can get, right? And so those are the ones that will enter in generating the momentum space lattice. The other ones can be generated by sums of those, so it should all work out. Okay, so that's why I've called these. Let me just do thing for this valley. So this is the eta equals 0 valley. And notice that at the eta equals 0 valley, the Qs that come in are Q plus, if you work it out, you'll see that the things that come in are the set Q plus Q1 and the set Q plus Q2. And so the momentum space lattice for eta equals 0 will involve the sort of blue and orange sites like this. For eta equals 1, it will involve the other pair going that way, and for eta equals 2, the third other pair. So if you like, the momentum space lattice actually has this principle of exclusion built into it. And so that's the Q lattice that you get, and that builds in some of the physics that we'll see. It kind of is important to think about the various symmetries. And so I'm going to call this set Q eta for each of them, right? So good. Happy so far? Yeah? Okay. So that's why the Q plus Q1 comes the following. So the color coding is a little confusing. So Q1 is Q plus Q. So if you look at this set, you're getting everything offset by the reciprocal lattice plus this displacement and so on. The next one will give you reciprocal lattice plus that displacement and then the third displacement. So you'll get all these, you'll generate all the different pairwise colorings. So the momentum space lattice is a Kagame lattice in this case. And in some sense, that's very satisfying because that's the third of the kind of family of triangular motif lattices. So you have honeycomb, Kagame, and triangular, so you get the Kagame now. Yep. Yeah. So it's this weird Kagame, but but once I put all of them together, it is Kagame. But you're right that it's Kagame, but you will see actually be a theme. In real space also, there'll be some Kagame-like structure, but that Kagame-like structure will actually hide, some hoppings will be switched off and things like that in real space. So you're right, already in momentum space, you see it's not perfectly, it is a Kagame in terms of the points, because if I, for the full reconstruction, I have to think all of them. But yes, you're right, for this pair, only this thing comes in. There are some, it is still 2D because there are sort of higher neighbor hoppings allowed and so on. So there are these kinds. Good catch. So if you like, the dots are Kagame, but if I squint at one valley, I don't see the full Kagame structure, at least for this little relaxation, and things can change things a little bit. It will be useful to think in some ways like that, but in the end, you could, I think we'll go to the real space thing, it'll be clear. Again, this is just an auxiliary thing for thinking about symmetries for the hopping problems. I don't want to spend too much time thinking about the symmetries of it. Kagame is just useful because it's just rigidly those are the points, and then there's some detail in exactly which hoppings enter when you do the reconstruction. But hold that thought, because it will be important to find triangular motif. Tomorrow's lecture will be important to find rectangles within triangular lattices or Kagame lattices. It'll be useful. Yeah. Happy? Everyone happy so far? Good. Okay. So these are the two things that I can say which are quite general, in the sense that, as I pointed out earlier, fixing the moiré reciprocal lattice and fixing the Q lattice are kind of things that we can do in generality based on just very abstractly moiré rotations and so on. The next two steps require us to think a little bit about symmetry in the moiré setting and doing some back and forth with some ab initio. And before we do any of that, we have to step back and think a little bit also about the actual materials involved. So we're going to take a little bit of an interlude and talk a little bit about the actual construction of these endpoint systems. One very interesting thing here is that they actually exist materials that we think will do this. So here is an example. So what we want is an exfoliable 2D material whose monolayer dispersion is near the endpoints. So there's now, thanks to the kind of collaborative efforts of the groups at Princeton, Sherbrooke, and in Donostia, there's a 2D materials database that you can look and search for things that can be exfoliable. So sort of combine some chemistry and physics principles to think of way to success. So there's a large list of things, and things that have stuff near the endpoint are kind of a class of things here like 1T TMD-like systems, and also some other material, gadolinium telluride, which has a different structure. I'm going to focus on a pair of these, actually really focus on one of these, 1TSNSE2, and say a little bit about zirconium disulfide also. So these are materials which have this sort of TMD-like structure. So you have either selenium or sulfur and tin or zirconium. And if you do monolayer chemistry on this, so what you do, look at the monolayer and you do some quantum chemistry, what you find is that the top bands, the ones that are involved in the moiré reconstruction, actually in the SNSE2 case are S-like molecular orbitals centered at tin, which are nice and isotropic. Relatively, the effective mass of the parabolas here will be very isotropic. Whereas for zirconium disulfide, you get DZ-like molecular orbitals of zirconium, And those will have a substantial anisotropy at the monolayer level. And that mass anisotropy will play some role in doing the construction. So by the way, from now on, I'll be relatively qualitative, because in the end, when you're trying to do a moiré reconstruction, at some point, you need to put it in a computer. And I don't know of a way to do it by hand, because the angles we're talking about are small. Okay? So a second piece is that you would have noticed that these materials have inequivalent A and B sites. And so there are two inequivalent ways you can stack. So you can have an AA bilayer that's stacked this way, or you can have various types of AB type stackings. In the AB bilayer, you can stack it this way. So there's sort of the picture over here. And what you see, what we'll find is that the two stacking configurations will give you different symmetry properties for the moiré problem. So in the two stackings, we'll have to think a little bit about how to implement symmetries while thinking about the moiré picture. So it's useful to just say some comments based on an approximate continuum model. So you can do some sort of preliminary ab initio type modeling. There's a nice trick that you can use, which is, of course, calculating a full twist structure is very costly. But what you can do is essentially realize for the small, what you can think of is that if you have a periodic array and you twist it a little bit, locally every twist looks like a shift. And there's some geometry that tells you what the shift is. So something that you can do is kind of read off a moiré problem by sort of, kind of doing a version, something like LDA, where you say there's a local density and you feed it in. Here, what you do is a local twist approximation. So you take a twist, make it into a kind of periodically modulated stacking picture, and then solve for the, and then what you do is you sort of interpolate between the solutions of different stacking configurations. And you can do different stacking configurations because those are crystallographic, right? You clamp them, you shift them, and you do DFT in the clamped configuration. So different stackings are not costly because they don't have a big unit cell. And so that local stacking way of thinking about it is useful. And so you get a picture for this H. Remember I said if you want to do the work, you have to write down the HQQ prime. So you get a simple toy model for this, which tells you that you have kind of trivial parabolic bands that start from some Q and Q prime points like this, with some TQQ prime, some interlayer matrix elements. And for the AA stacking, so these hopping QQ prime are these hopping elements. For the AA stacking, the momentum space hoppings have this form. For the AB stacking, have this other form. I just wrote this down for completeness. The details aren't important, but you can read off these parameters from ab initio, and so you get these sort of MX and NY parameters, and what you see is the effective mass anisotropy is substantially larger for zirconium disulfide than it is for SnSe2. There's a caveat that the 3-parameter models don't actually fit so well, but you can enhance this. I just did this for simplicity. I didn't want the equations running off the page. You put a few more parameters, you can get actually a pretty good match to the DFT data at 3.89 degrees. So just saying that this is, you can do this with some reasonable accuracy. Okay? So I just want to now say a few qualitative things about the important symmetries that play a role in this problem. Okay? So it turns out, rather surprisingly to me, who had thought about this for a long time but never thought I'd see it in momentum space, for endpoint twisting, a new kind of emergent symmetry is important in organizing moiré reconstruction, and something called a non-symmorphic symmetry. Let me say a little bit about it. Usually these are symmetries that exist in 2D real space. They're symmetries of 2D crystals that are very important, and I thought about these about a decade ago because they're useful in coming up with generalizations of the Liebschull-Mattis theorem using these kinds of symmetries. But in 2D, in 2 or 3D real space, and in 2D, there's a unique type of non-symmorphic symmetry, which is a reflection followed by a partial lattice translation. So for instance, if I had a picture like this, I reflect and do a partial translation, right? So you can see that that's a symmetry. Neither on its own is a symmetry, but their composition is a symmetry. Mathematically, this is because some space groups are not the semi-direct product of their point group and their translation group. They contain elements, that quotient is non-trivial, and elements in the quotient are not symmetrically generated. So that's sort of a mathematically technical way of where these symmetries. Now, these are symmetries of real space. They're kind of standard. They give you kind of usual, they give you some interesting results, but they usually never exist in momentum space. And a different way of saying, and maybe a way to think about that is, in real crystals, the reciprocal lattice, the momentum space lattice that you have is always a Bravai lattice. So there's no way to get this kind of symmetry. But now we have kind of non-Bravai structure. This is not a rigorous statement, but because we have this sort of non-Bravai structure, maybe we can get some of that structure in momentum space. That's not technically true because neither the Kagame nor the triangular lattice are themselves, or the honeycomb lattice are non-symmorphic. They're both symmorphic lattices, so it's not a direct analogy. But maybe it's less surprising that these symmetries will play a role. In momentum space, if they come in, they're only usually relevant for a large magnetic field where magnetic translations are playing a role. So it turns out if you do this M-point problem, you can sort of, and I'll talk about the detailed origin in a little bit, they end up having such a symmetry. So it's what does it mean? So remember what I did was do a reflection and a partial lattice translation. What a momentum space non-symmorphic symmetry is going to do is do that, but on the momentum space lattice. So what it does is do some kind of reflection on these C's, but also boost them by some Q. So notice that there's something like this. There's a sort of mirror symmetry. It's maybe easiest to see what it does in real space, and this should have been a minus L. I apologize for the oversight. So what it does is swap the layers. So it does a reflection between the layers, but then also boosts the momenta. So it does something quite non-trivial. In real space, what you can see is it flips the layers, and I think I might have a typo here. There should have been a shift here, R plus, and there should have been a phase factor. Sorry. Okay. So let me go show you let me give you a picture of what these symmetries can do when they act in momentum space. So let's do a 1D toy model first. I have a ladder model with a pi flux through every square of the ladder. Okay. So of course that means that the actual unit cell of this model is 2 pi. But if I look at it, there's pi flux, so every site looks like it has the real a similar type of environment. So maybe there's some consequences to that. And so the way this acts is, so T is translation. Translation acts in a standard way. It just boosts you to the n+1 point. The mirrors, this non-symmorphic mirror symmetry says if I reflect, it turns out that you can show that the role of reflection, because there will be phase factors on these hoppings, is that you reflect, you swap the layers. So layer L goes to layer minus L, or plus to minus, minus to plus. But you pick up a phase factor of -1 to the n that checks whether you're an even unit cell or an odd unit cell. And if I translate that to momentum space, what it says is that Bk in layer L must be connected to k plus pi in layer minus L. If you translate that into the kind of hopping problems that you can write down, what it says is that the sort of hopping has the symmetry enforced, so k and k plus pi are matched to each other under the hopping. That just tells you certain hopping terms can't be written down, so it's this sort of symmetry in the hopping. In 2D, what we can see is that this M twiddle Z, if it's an exact symmetry, will forbid certain hopping. So this goes back to a picture somebody asked. If I think the eta equals 0 valley, but now in real space for the AA stacking configuration, so the reason the stacking is important is it's for the AA stacking where this MZ exists as an exact symmetry. In other stackings, it doesn't. Because it shifts the layers, whether the symmetry exists or not is sensitive to the stacking. We'll see how this can arise in a minute. The MZ axis is parallel to Y, and you can show that in this coordinate system for this particular valley. And you can show that, it commutes with one translation and anti-commutes with the other translation. So if I think about what this means for the states, it means that I can actually partition my system in these colors into sites with a different eigenvalue of this MZ operation, and there can be no hopping between these two different sites. So the naive nearest neighbor hopping on this problem is forbidden, and the actual hopping is actually like this rectangular lattice rather than this triangular lattice. And so that's the most powerful symmetry. Now, it turns out this can often be very useful because this is just a symmetry property, but also because I started out near the M point and the way the moiré reconstruction works, it will turn out that in many cases, the leading nearest neighbor hopping along the vertical lines will be very strong, and the crossed hopping horizontally will be very weak. So there's already an anisotropy built in. And so if I have that and I cut off the blue to orange hopping in this picture, then I get effectively a quasi 1D dispersion. So these kinds of symmetries, because they suppress certain hoppings, if combined with the right other set of parameters, can enforce quasi 1D behavior. And so that's something that we'll come to in a couple of minutes. Okay? So these the results so far were really coming from this approximate continuum model and thinking about it. It turns out actually the approximate continuum model while it worked quite well, the Bistritzer-McDonald model works very well. For these M-point materials, that toy continuum model I worked is rather too rich. For instance, the bands do not disperse at all along some direction, or do not have any moiré reconstruction on some direction, have full continuum symmetry. So they're a little too simplified, partly because the way I drew the Q lattice, there are other details you have to put in. But if you do a little bit more work, they're useful. They give you some symmetries, but you can generalize them by asking, let's just think of the moiré potential consistent with all the symmetries, work with that and think of the constraints, and that gives you a better guide. So what I'm going to tell you is a summary of that. And in particular, at small twist angles, we can actually think about the kind of good emergent symmetries, what I'll call zero twist symmetries. They're a little bit like if you know about particle hole symmetry in TBG, that's sort of an example. So TBG has a very good approximate particle hole symmetry. And the way to make it exact is to just ignore the fact that when you rotate a Dirac point, even though Dirac point looks isotropic, when you rotate it, the wave function changes a little bit. If you drop that effect, you get particle hole symmetry. So it's these sort of symmetries that exist because the twist angle is small are good approximate symmetries. And so there's a lot of them. There's a long story, but let me just focus on these special non-symmorphic ones. If I have AA stacking, it turns out that the monolayer has an inversion symmetry. But if I translate that into the moiré problem and think about how it acts on the moiré bands, this becomes a mirror symmetry, which is non-symmorphic on the moiré problem. In the AB stacking, you have a mirror in the monolayer, and that becomes an inversion symmetry when it's translated. That sends K to L to a shift minus K plus a shift and minus L. That's how the inversion works. Now, this looks like nothing like this one, but it turns out there's an approximate moiré C2Z symmetry, and their combination gives you an approximate mirror, roughly speaking. And this is not as ideal because it relies on this approximate symmetry here. And, these exact symmetries actually get spoiled by relaxation, and there's this weird paradox that even though these are small twist symmetries, the relaxation is very bad at very small twists. So that, where they should be getting better, they get worse. So it turns out at about 3.8 degrees is a sweet spot where they work pretty well. The angles are small, the relaxation is not so bad, but it's still small enough that you can use the small twist symmetries. So that's quite a sort of a nice feature there that this is good. Okay, so that's how we think about the symmetries. There's a lot more that you can do. I just want to sketch the important ones. You can refer you to the very long supplement for details there. So let's just say a little bit about how the band structure calculation works. I meant this already. If you do just the continuum model Erlab-Bistwitzer-McDonald, so that another ingredient in Bistwitzer-McDonald is the statement that the interlayer tunneling between sites R and R prime only cared about the distance between R and R prime and not the detailed path that things take. Of course, this is an approximation, but this was a powerful one that was done by BM. And the second is to keep the first harmonic. And if you just do that, you get sort of an accidental symmetry with continuous translation along one direction. So you're going to have to do more general moiré potentials, but be symmetry constrained to get new results, right? And just to recap, that the non-symmorphic symmetries are the ones we should think about. They're the most important emergent symmetries, and they're important even when they're kind of approximate. And as I said, they can help to make the system quasi-1D, but they're more fundamental. And an important point is that, people have thought about generalized twist angles before, and those simplified models suggest that sort of quasi-1D behavior is quite general for twisting the endpoints. But it turns out reality is trickier. So for instance, if your monolayer had some anisotropy, an anisotropy that naively would look like it made the system more one-dimensional. So it's like bands are lighter in one direction and very heavy in the other direction. So it's as though hopping is easier in one than the other. Turn out to actually suppress quasi-1D because the way they interplay with the moiré problem is not intuitive. So you have to sort of think more detailed way about these things. And relaxation, as I said again, plays an important role in modifying some symmetries from exact to approximate and thereby kind of creating modification. So just to flash that you can do ab initio, so I'm going to pick a material now. For both AA and AB stacking, you get flat bands at a twist angle of about 3.89 degrees, which is sort of a nice one that people use. For both the AA and AB stacking, I've highlighted these here. And there are 6 bands, because there's 2 spin and 3 valley bands. And it turns out that spin is a good quantum number, so you have SU2 spin rotation symmetry. We have the 3 valleys because of the 3 endpoints. They're topologically trivial. And so you can Warnierize these bands to get an effective tight binding description, right? So that's something we can do. And so let's think of the real space picture. The real space, when you translate back to real space, where the orbitals are placed in real space for these endpoint materials in the Warnierized model depends on the stacking. And the interplay of the orbital placement with the symmetries influences the hopping. Exactly where they're placed and how close they are is whether that fact that some hoppings are extinguished, is that useful or not, depends a lot on where the orbitals are placed. So for AA stacking, what you find, what you can see here, is that the orbitals from the three valleys nearly coincide. So they're almost on top of each other, and they form a triangular lattice effectively, although I've drawn it sort of poorly. So you see that I've drawn a hexagon here, but really what you should say is that there's actually a triangular lattice because I'm only occupying one corner of this hexagon, right? So there's a triangle. I just stole this from a figure. We're just trying to show something else. Apologies. And what you see is that I've colored these orbitals blue, red, and orange in this. And what you see is the orange orbitals really only hop along this direction. The blue orbitals really hop along that direction. The red ones only hop along that direction. So what you have this is valley selective 1D hopping. It's quasi 1D because they're weak higher neighbor couplings. But basically the immediate first neighbor coupling is ruled out by one of these symmetries. So you have to go to the second neighbor, which is much smaller because the orbitals are so far apart. And we'll see in tomorrow's lecture that this enables kind of very nice set of quantum Monte Carlo simulations that allow us essentially exact numerical access to this problem. AB stacked version, which I'll have much less to say about, has orbitals from all three valleys that are displaced from each other sufficiently far. So I push these aside enough that what I get is a Kagame lattice. So the reason these hexagons are drawn is to show where these orbitals get pushed to. So I push the blue up, the red that way, and the orange that way. And you sort of see that what you find is something effectively like a Kagame. So you can see the sort of four stars of the six triangles pointing out of the Kagame here. And this is a 2D problem, but it has this weird feature that there's no nearest neighbor inter-valley hopping, and that makes it different from the usual Kagame. So that's sort of a rich story there. So I'm a little bit ahead, but let me just close with a summary. So twisting the endpoint has sort of opened a new array of moiré materials. And the easiest way I know to understand the single particle moiré problem in this setting is by studying this momentum space hopping problem. So what I argued was that there's this Q lattice approach that works in the language where in each layer, I measure momenta in each layer from their low energy dispersions. So from the M point or the K point or the gamma point as the case may be. And then what we find is that there's a momentum space lattice that's generated by the reciprocal lattice of moiré plus a basis that's given by the differences between those minimum points of the microscopic Bravais lattice once they're rotated. And the emergent momentum space non-symmorphic symmetries actually play a key role in organizing our understanding. And I mentioned two examples in SNSE2, the AA stacking, which gives you a triangular lattice with quasi 1D hopping, and the AB stacking, which gives a Kagame lattice. And so what I'll do tomorrow is talk about how we might approach thinking about this AA stacking problem by a variety of numerical tools. Okay, let me thank you there.
So I think one of those, you actually, you're all of what you are, a little bit.
Happy to stop there. Maybe if there's something right now with some, yeah. There were a lot during the lecture.
That's still the active